Hello everyone, welcome to the talk on how to break PDF encryption. My name is Jens Müller, I'm a PhD candidate at the Chair for Network and Data Security at the University of Bochum. And today I will give you an introduction to our research, which is a joint work with the University of Applied Sciences in Münster on security flaws in the PDF encryption standard, which we call PDF exFiltration or PDFex. Now, what is PDFex? Some of you may have heard about it. It's yet another attack that comes with a logo. And PDFex introduces two novel attacks on PDF encryption, which I'm going to present today. Both are weaknesses in the PDF standard, and both were actually found by carefully reading the standard. One based on flaws in the PDF data format structure, which allows for partial encryption. We call this attack direct exFiltration. The other one is based on actual crypto, so on flaws in the used block cipher modes of operation. We call this attack Malleability Gadgets. Here's an outline of today's talk. First, I'm going to give a short introduction to PDF and who actually uses PDF encryption. Then I'm going to introduce our attacker model and show our first attack on how to directly exfiltrate the plaintext without even touching the crypto. Then I'm going to show our cryptographic attack, CBC Malleability Gadgets, and how to practically apply them, as well as an evaluation of those attacks on 27 popular PDF viewers and existing countermeasures. But let's now start with some facts on PDF. So we are all familiar with PDF, the portable document format, a de facto standard for electronic document exchange. PDF was developed in the early 90s by Adobe and is an ISO standard since 2008, with the current version being PDF 2.0. According to Adobe, 250 billion PDF documents have been opened in their products in one single year, so that's where all our telemetry data goes to. So it's fair to say that PDF is used in almost every company and institution out there, and PDF is a rather popular file format, right? Now, PDF also supports AES-based document encryption using either password-based or certificate-based crypto. So AES, well, it's considered pretty secure, right? So if someone breaks AES, the sky's falling anyway, right? So we are basically done here. We can give up, and thanks for listening. Questions, anyone? Okay, of course, we did not yet want to give up. So instead, we thought, let's have a closer look on how encryption is actually applied in the PDF standard. Did they do it correctly? And if not, what could possibly go wrong? But let's first answer the question on who actually uses PDF encryption. For example, our local German bank does. So they know that a lot of their customers cannot handle PGP or SMIME. Therefore, they send you sensitive data as encrypted PDF documents within an email, while the password is sent over a second channel, such as SMS. And there's also companies that allow you to directly do this in the email client, so they sell you plugins, for example, for Outlook, and encrypt PDF or encrypt email content as an attached PDF file. Then also MFPs and scanners, they allow you to directly encrypt the scanned document, which is an interesting feature, especially if you want to use functions such as scan to email. Last but not least, PDF encryption is used by companies and governments worldwide. For example, by the US Department of Justice, they use PDF encryption as the default way to file claims. So we thought, okay, that's worth having a deeper look at PDF encryption. But let's first define an attacker model. So assume Alice wants to send a PDF document to Bob. She's going to encrypt the document because the communication channel is not to be trusted. This could be email, for example. Or assume a shared storage service where Alice uploads the document and Bob later on downloads it, but there may be a third party, for example, other users that have access to this storage. In such cases, we cannot rely only on TLS, we need end-to-end encryption. So using PDF encryption is a logical candidate for such workflows. Now, what is our attacker allowed to do? Our attacker is an active man in the middle who can perform targeted modifications of encrypted PDF documents in transit or at rest. He can now change the document structure or manipulate the ciphertext itself, for example by flipping some bits before forwarding the modified document to Bob. The goal of our attacker is now that when Bob opens the modified document with his password, he leaks the plaintext to an attacker-controlled server. We assume that a really strong password or even public key crypto is used, so trivial attacks like brute force, they won't work. It is important to note that this is not an offline attack. So this is a man-in-the-middle attack, but the only reason to actually use end-to-end encryption for your data is that you assume that the communication channel is maybe not trusted and there may be some malicious party in the middle. Okay, so how does PDF encryption technically work? First I need to give you some PDF basics, which will then result in the direct exfiltration attacks. Let's first have a look at the simplified structure of a PDF document. So a PDF document consists of 4 parts. First, there's a header, which contains only one line containing the PDF version, like 1.7, for this document. And there's a body containing the definition of all the pages within that document, as well as the actual content. So that's the most important part. There's a cross-reference section, which contains an indexing table that defines the offsets of all the objects within the document. And finally, we have a trailer which contains some more information, such as a reference to the root element of the document. So PDF documents, they're actually processed from the bottom to the top. Now let's encrypt this very PDF document and observe the differences. Now that looks interesting, right? Not everything is actually encrypted. All what happened here is that an encrypt object is added down there at the trailer, which contains some information such as the encryption scheme to be used, for example, AES 256, which is important for decryption, of course, to know which algorithm is used. And the only objects that are actually encrypted are those objects that contain the actual document content. But the document structure is actually not encrypted, even for an encrypted PDF file. Why is this? Let's have a look at the standard. So the PDF standard says that all strings and streams are to be encrypted, but not other object types such as integers or Boolean values. The reason for this is efficiency. So random access to all objects in a document, even in encrypted documents, is to be granted. Okay, fair enough. So what does that mean in practice? Basically, it means that the whole structure of PDF documents remains unencrypted. Only strings and streams in a document are encrypted, while those object types contain the actual content, to be fair. But in other words, a passive attacker who obtains an encrypted document can already reveal a lot of information, such as, for example, the number and size of pages and contain objects, maybe even if there's hyperlinks and so on. So from a security perspective, this already looks interesting. But maybe there's even more. Let's once again have a look at the standard. So in 2003, PDF introduced crypt filters in order to provide a finer granularity control of encryption within a PDF file. What does that mean in practice? It means that not all content streams in a document have to be encrypted. You can create a document of which some content streams or strings are encrypted and others are not. There may be legitimate use cases for this. But this also means that every standard compatible PDF viewer must support partial encryption. So in other words, an active man-in-the-middle attacker who can modify a document can add and mix his own content to an actually encrypted document. And there's not only crypt filters, actually there's 18 different techniques to do so, which we found by carefully studying the specification. So it's really hard to implement a PDF viewer that does not support partially encrypted documents. Okay, so an attacker can easily add new content to encrypted PDF files. You may now say, well, fair enough, the standard claims protection for confidentiality, but not for integrity of the document. So the question arises, can we do more? Can we do some targeted manipulations? Can we maybe use this technique to somehow actually exfiltrate the plaintext by modifying the document structure? Well, let's have a look at the standard again. So if you search the PDF specification for a document's possibilities to communicate with the outside world, you will quickly spot features such as the submit form action. So PDF files, they can contain forms, and the form content can be submitted to external web servers similar to HTML. Now, the PDF standard specifies that the same data types are used for the content to be displayed and PDF form field values, and that's really interesting because the value of a form, as the standard states, can be any reference to any stream or string within the document. Wait, strings and streams, that's exactly the only content types that are actually encrypted in a PDF document because they define the actual content of the document. So we thought, well, why not add a form button to an encrypted PDF file that references to encrypted parts like strings and streams, and then exfiltrate them as form data values once the user somehow clicks into the document, clicks on a submit form button. Then we read the standard again and we thought, well, clicking on the button is lame. Why not submit the data automatically once the document is opened and decrypted by the user, which can be achieved, for example, by launching the submit form action with the open action event of a PDF file. So let's put all this together. What you can see here is the body section of a PDF document with two objects. Object number 2 is basically the encrypted data. The attacker has no knowledge of this data, but he can add another unencrypted object, object number 1, where he adds a PDF form, which submits basically the object number 2. So the PDF form field content is a reference to object number 2, and the form is automatically submitted using an open action once this document is opened and decrypted by the user to the domain p.df. Okay, and once the document is opened and decrypted, we would see the actual plaintext of that stream being submitted to the domain p.df. Now, this is not a theoretical issue. Let me show you a demo for Adobe. So what you can see here is an encrypted PDF document. And now we manipulate it and we say that all streams remain encrypted, but all strings use the identity filter, means no encryption at all. And then we add our own structure, our own objects here, and we add an open action event that submits to evil.exepsilon port 8080, and basically we define the encrypted part, the object number 4, as a form value to be submitted to evil.exepsilon once the document is opened and decrypted. Okay, let's use Netcat or whatever on our evil.exepsilon server, and let's open the document. And Adobe will ask us for a password. And once that happens, it will once again ask us if we should submit the data to evil.exepsilon, and if we accept this, the plaintext will be submitted to our malicious server. So interestingly, this requires some user interaction in current versions of Adobe. However, the first 256 bytes could already be leaked without any user interaction because a DNS lookup is already requested before the user has any choice to click yes or no. But it requires user interaction if you want to leak a lot of data in current versions of Adobe. But in most PDF viewers, we could actually achieve this without any user interaction at all. I will come back to that later in the evaluation. Okay, and there's also some other options. So for example, you can use hyperlinks, which are technically UI actions in PDF. And basically you can say, well, I have an unencrypted string, for example, which is a URL, http p.df, and then I define any stream in the document as a string, and basically I use a base URL like p.df, and then as the URL path that is to be used, so a relative URL would be the encrypted part. So we could basically make the user click on a hyperlink, or automatically using OpenAction or whatever trigger a hyperlink. So this is a bit less silent because the browser will open in most PDF viewers at least, but it's another technique to achieve basically the same effect. And there's even one more option. There's JavaScript if supported by the reader. You can also use JavaScript to access the encrypted part from an unencrypted part, from a JavaScript action basically. And then you can also use JavaScript to basically leak the data. So there's basically those three sub-attacks that allow you to achieve the exfiltration of data. Okay, so much for the easy attacks. I call them easy because they can be easily detected by having a closer look at the PDF document structure, right? So we thought, can we do maybe more? Can we maybe even modify the document's plaintext content by performing targeted modifications at the ciphertext level itself, resulting in Malleability Gadgets that some of you may know from the eFail attacks. So you might remember the eFail attacks on PHP and SMIME back in 2018. Let's see if similar attacks work for PDF encryption. And the original eFail attacks, they basically had three requirements. First, ciphertext malleability. So the attack is currently called Malleability Gadgets because we need ciphertext malleability, and we've got no integrity protection in the PDF encryption standard, which is pretty good for an attacker. Second, we know some kind of known plaintext to actually perform targeted modifications. And third, we need an exfiltration channel to basically leak the plaintext to the attacker. And well, we already have that because we can reuse the exfiltration channels that I've shown you previously, like PDF forms, hyperlinks, and JavaScript. So we can already check this box, right? Nice. Let's talk about ciphertext malleability and what we call gadgets. So this is, as you probably know, the decryption function of CBC, the cipherblock chaining mode, as used by PDF encryption. And in the upper part, you can see the ciphertext blocks C0, C1, and so on. And in the lower part, there's the plaintext blocks. So decrypting a block of ciphertext and then XORing the previous block of ciphertext onto that will result in the plaintext block. So let me ask now what happens if you decide to change a single bit in the ciphertext. For example, let's flip maybe the first bit in the initialization vector, and if you do that, the very same bit will flip in the resulting plaintext. Now, what happens if we could somehow know the content of a whole plaintext block? Then we could XOR that onto the very first block to get all zeros, or what we basically call a gadget a blank sheet of paper, because we can write on that by taking any chosen plain text and XORing that to get this plain text as a result. And this way we can, for example, construct URLs within the actual plaintext by performing targeted modifications to the ciphertext blocks. What we can also do is move those gadgets around, clone them, move them somewhere within the document, thereby having multiple gadgets. But remember, if you do that, there's always the avalanche effect of CBC, so you will get some random bytes in here, but the URL still remains in place. So now that's ciphertext malleability done. Now all we need is some piece of known plaintext. As the PDF standard has been very helpful so far, maybe let's have another look at the PDF standard for encryption and see if we can find something. And we found PDF permissions to be very promising here. So for PDF document you can set certain permissions, like if the users are allowed to print them, for example, or if users are allowed to copy a text from them and so on, which is technically done by adding a dictionary key and the value for permissions. And soon after that, people started tampering, of course, with this permissions object to basically be able to print their documents or foreign documents. Therefore, Adobe added an additional encrypted version of those permissions for encrypted document. So basically, they added a 16-byte blocks, which contains 4 bytes of ones to allow space for further flags. So the first 4 bytes of the encrypted permission strings always ones. And then there's the p-value, which is the actual permission, so you can find the unencrypted copy within the document. And then there's 1 byte that says TOF, that states if the metadata in the document should be encrypted, which you can also see from the document, so that's also known plain text. And then I leave it up to you why they added a static string that says ADB. And then they had no more ideas and they added some random bytes to fill it up to get 16 bytes. But this means that we have 12 bytes of known plain text by design. Okay, which is pretty bad. So to sum this up, Adobe decided to add permissions to PDF documents. Then people started tampering with those permissions. So they decided to encrypt those permissions to prevent tampering. And now there's known plain text available to attackers. So basically we have all ingredients to perform CBC Malleability Gadget Attacks. This allows us to, for example, change the displayed text in otherwise encrypted documents, things that we could previously also do by modifying the outer structure by adding new unencrypted objects based on partial encryption, but we can also do this now using targeted modifications of the ciphertext. And this allows us to, for example, modify stream content within an encrypted content stream through the encryption itself. All we need to do is somehow comment out the random bytes that are now in there due to the avalanche effect. And basically this results in content being injected into otherwise encrypted documents. And those 12 bytes of known plain text, they're enough to not only change the text to be displayed, but also to perform exfiltration attacks using those 3 sub-attacks forms, hyperlinks, and JavaScript by, for example, define the URL of a new form to submit it to a URL, at least if you register a very short domain or if you want to guess additional plaintext characters. So this is basically the same sub-attack using PDF forms, but this time the URL where the form is to be submitted automatically once the document is opened and decrypted is also basically encrypted, and some targeted modifications have been performed using Malleability Gadgets to submit the plaintext to a certain URL. Okay, also this is not a theoretical issue. I can show you a demo in Chrome, for example. This time also works for Adobe and for each PDF viewer that supports encryption basically. So what you can see here is an encrypted PDF document opened in the Chrome browser. We have to insert our super secret password to get the super secret content that says hello world. And now we can't do this attack manually, so we have written a small Python script to automate the Malleability Gadget attack that basically takes as an input the encrypted PDF document, creates a gadget based on the known plaintext, based on the permissions, and then adds an exFiltration channel like a PDF form and writes to a modified encrypted document. Let's reopen this modified document with Chrome. Once again, we open our first of all, let's start an HTTP server, of course, to get the exfiltrated content. Let's insert our password, and what you can see here is that the whole object is exfiltrated automatically once the user inputs his password. And you can, of course, use not only those Malleability Gadget attacks to add PDF form URLs, but also to prepend URLs to existing plaintext, and then use, for example, hyperlinks to achieve the same effect. And you can also use JavaScript. So all three attack variants, they can also be used in combination with CBC Malleability Gadgets. Okay, now let me come to an evaluation of those both attack types. So we tested 27 popular PDF applications that were assembled from public software directories for all the major platforms, Windows, macOS, Linux, and web browsers, which also support natively opening PDF documents. So this list should contain basically every PDF viewer that supports PDF document decryption. And by design, each and every viewer should be vulnerable to both direct exfiltration and Malleability Gadgets. In practice, 4 of the tested viewers did not support the full specification of the PDF standard, and therefore we could not apply direct exfiltration attacks to them. But for a vast majority, direct exfiltration attacks work, and for all of them, Malleability Gadgets do work. Now for some of the attacks, the half circle, the user is required to click somewhere within the document or click on a link in a document, while the full circle does not require any user interaction at all. Okay, now let me come to mitigations and maybe actual countermeasures to prevent those attacks. So one mitigation strategy would be to use existing methods to add some kind of integrity check. So both the Malleability Gadgets and the direct exfiltration attacks work because the attacker can modify encrypted documents either through the ciphertext or the outer document structure and object structure. So why not simply use the optional feature of PDF signatures to prevent such attacks. Does it work? No, it doesn't work in practice, unfortunately, for 3 reasons. First of all, broken signature does not prevent the victim from opening the modified document and thereby exfiltrating the document. Second, PDF signatures, they're actually rarely used. They are optional, they're not mandatory. And for encrypted documents, the signature is not encrypted. The signature is added as plain text. You can simply strip it. And if you like to, as an attacker, you can also re-sign the modified document under your own identity. And finally, parts of our team broke PDF signatures last year, but that's another story. Another mitigation strategy that could come to one's mind is closing backchannels. So you could not exfiltrate the plaintext anymore. In practice, this is really hard to do, as it seems, because the 800 pages PDF standard allows various ways to open a connection to an attacker-controlled server to basically phone home without any user interaction, but also with user interaction. Let's ask ourselves if we want to remove, for example, clickable links to a URL within a document, which is really a standard feature. Do we want to remove PDF forms? Do we want to remove JavaScript? And maybe we want to remove JavaScript. Okay, so at least we should try to ask the user before connecting to a server that may be a mitigation strategy, but it does not solve the root cause. So short-term mitigations applied by Apple was to, for encrypted documents, ask the user for each and every link that is clicked if he really wants to access that URL, and also show the whole URL including the path to prevent leakage of a plaintext. And what Google said for Chrome is, well, actually we give up and stop trying to fix the unfixable, because they realized, it's actually a problem of the standard. So what could we do to counter those attacks? To counter direct exfiltration attacks, we could remove support for partial encryption, preferably in the standard itself. In the short term, implementations could try to implement some kind of mixed content policy for the web and adapt that to their PDF view applications. So unencrypted objects, they should no longer be able to access encrypted objects. And to counter CBC Malleability Gadget Attacks, we could move from non-integrity protected CBC mode to some kind of authenticated encryption scheme, but also be careful here to prevent downgrade attacks. This is something for newer versions of the standard, and actually this will be escalated to the ISO working group on crypto and signatures and will be taken up in the next revision of the PDF specification, is the answer that we got by Adobe. Okay, so let me come to a conclusion. So PDF encryption can be broken in the scenario of an active attacker. And PDF is one of those data formats that supports partially encrypted documents, which is considered dangerous and allows for direct exfiltration. Also, PDF uses legacy crypto as AES CBC without any integrity protection instead of modern authenticated encryption schemes. And the last version of the standard even has known plaintext by design, which allows for gadget attacks. And finally, interestingly, PDF is a data format that allows to exfiltrate itself to an attacker-controlled server. Okay, thank you. You can find all the exploit files on pdf-insecurity.org, and there's also proof of concept files on how to forge PDF cryptographic signatures in all major viewers. Okay, thank you and enjoy the rest of this virtual conference.